Okay, let's start with the webinar related to the power control of the three-phase grid converter, connected inverter with a SmartCtrl. So in this webinar, we have a three-phase inverter. These topologies are widely used in applications such as motor drive, UPS, and renewable energies, and others. This control structure has two current loops, one for the axis, another for the Q axis, and the current is imposed by the active and the reactive power. So we start with a PSIM simulation. The first step that we will get the frequency response of the current plan using the AC sweep function. Then we export the TXT file to the PSIM to the SmartCtrl. In SmartCtrl, we tune the PI compensator for the both current loops, and then we copy the parameters of the PI, the key P and the TI for the to PSIM simulation, and we will check if our converter is stable or not. So this is the control structure of the simulation. So we have a DC component in the input of the switching cell. We have just a L filter, and it's connected to the grid. So also the switching frequency that will be considered is around 50 kilohertz. And also we have two loops, one in order to control the D current and other for the Q current. So this is the power reference generator. This expression will get from the definition of the DQ power, the DQ power definition. So this is the expression that we can get the reference, the D current reference and the Q current reference. So just we have to clear from this expression the IQ term, and then we have to replace in another expression, and we have to clear the another current. So this is where we can get the current reference. So after then, I will open a PSIM template. So this is first. Okay, let me run the simulation because it will take some minutes. Then I want to explain a little thing. So here we are sensing the grid voltage. Then we have a park transformation in order to get the DQ voltage, and also for the current. So here we are sensing the current, the inductance current, and then we have to transform to the DQ frame. So also in this simulation, we are not considering the phase looked loop. So in this case, we are just put a triangular source that it's going, this is the frequency, 50 hertz, and it's going from 0 to 2 pi. Okay, after that, this is the modulator. We have a PWM modulator. And also, this is the open loop, the operating point of our converter. So we have a one value for the modulating signal for the axis, and the same for the Q axis. And in the Q axis, I inject some perturbation. So this is the AC source that the name have to be the same for the AC sweep configuration. So we have the same name as the source, and our SIP start from 100 hertz to 20 kilohertz. So this is the amplitude of the perturbation, and that's it. And also, finally, I put the AC sweep proof in the EQ current. So the plan that I get is the modulating signal Q to Q current. So let me see. This is the frequency response that we get from the AC sweep. So after that, I have to go to the file, no, edit, view data point, file, save as. So here I want to set a name, GAQ. Click on save, and then I have to open a SmartCtrl. Let me close this. So let me open SmartCtrl software. Okay. This is the initial dialog. So in this case, I have to select the import frequency response data from txt file option. Click on here. And then I have to select one of the type of control that I want to design. In this case, it's a current mode control. Click on OK. And here I have to select the txt file that I saved before. So this one, click on open. And now we have to define the switching frequency. In this case, is 50 kilohertz. And in the current reference, it's like 20 amperes. So click on OK. This is the design flow. We have to select one of the sensor option. In this case, I select the current sensor. And here you can define the gain. In this case, I select 1. Also, if you take the transfer function for this point, you already consider the gain of the sensor. So because it's after the sensor, this is the current, the sensed current. So in this case, I have to select a gain of 1, click on OK. And in the compensator, as I mentioned before, we have different type of compensator, the type 3, type 2, type 3, PI, and equation editor. So in this case, I select just a PI because it's a first order system. And here, I want to show you, here we can define the modulator gain, the gain of the modulator. So in this case, in SmartCtrl, the modulator gain is calculated by this expression, but it depends on the peak value, the valley value, and this is the rise time, and this is the switching frequencies. So in order to get a gain of the modulator equal to 1, I have to set the peak value equal to 1, valley value equal to 0, and the rise time equal to the switching frequency. So that I mentioned before, this is 1, 0, and here is 20 microseconds. So click on OK. After that, this is the solution map section. I have to click on set. And here, I mentioned before, this solution map represents the relationship between the crossover frequency and the first margin. So the white region ensure that our solution will be stable. So in this case, I select 1 point, for example, here, 6.5 kilohertz and 50 degrees of phase margin. Click on OK, and finally click on OK. So this is the pink trace is represent the open loop transfer function, and here you can see this is the crossover frequency, and also you can see the phase margin here. So after that, the information that we need is the parameters of the PI. So in PSIM simulation, so I want to clear the open loop. So I have to add the PI compensator here. The value is 37.675 milli, and the another one is 30.952 micro. Okay, so let me copy this element again. So this is one for D axis and another one for Q axis. Then we have to calculate the error. So here, this is the error. So we have to copy the label for the sensed current for the axis and the same for the Q axis. Okay, let me clear the AC Swift proof and the SSF configuration. So another thing that I have to put in the simulation is the PQ reference generation. So I want to copy this. Okay, then we have to copy the DQ reference and IQ reference. So let me increase a little bit the total time. Okay, and then click on simulate. So this is the DQ current reference generator. So we set active power from 5 kilowatts, and then we inject some step in the reference of the active power. So the finally active power is 15 kilowatts. And in the same way, we start a reactive power from 0 to 10 kilos. In order to check if we are injecting the active and reactive power that we want, so I put here some bathymeter in order to see the active power, the measure active power, and also for the reactive power measure. So let me see that the simulation is now finishing. And we can check if our design is stable. Okay, so let me check the measure active power and the active power reference. So here you can see that the active power achieved the reference. In the same way, for the reactive power, again, the reactive power achieved the reference, and also we can see the three-phase current. For example, here, this is the three-phase current, and also let me check if the modulating signal are not saturated, because the triangular the carrier signal is going from -1 to 1. So that is all. And if you have any question, please let me know.